Okay, welcome to another Ginger Mathematician video. So again, I thought I'd look at some IB content, particularly on the high-level applications course that I'm currently teaching. And one thing I noticed looking at YouTube was there's not much content out there for the HL applications course. And in particular, looking at non-linear modelling. You'll find that the linear modelling is done on both applications courses, standard level and high level, but the non-linear modelling is not really well served on YouTube, and I thought I'd put together a three-part series that goes through everything you need to know about non-linear modelling for the high-level applications course. Before I start, please like, please subscribe, please crash and mash that subscribe button to make sure you make YouTube aware that this content is great. Right, let's get started. Now, the examples and the information I use come from the Hayes and Harris high-level applications textbook. This is the really big purple one, it's about 800 pages long. It looks very, very scary, but there are some good topics, there are hard topics and easier topics in there as well. And what we're going to focus on is power models in this video. The next video will focus on exponential and logarithmic models, and then finally we're going to combine that all together in my third video where we have a set of data and then we need to work out which model is appropriate and how to work it out from there. So a power model can be defined as the form y equals ax to the power of n, where a is greater than 0 and n is not equal to 0, otherwise that would just give you a straight line. And this is the way that the model is written. Okay, so x is our variable here and a and n are just constants. So one thing we can show is by using logarithms, we can see there's a logarithmic relationship between the x and y in this model. So if we take y equals ax to the power of n, and just add the natural log to both sides, which is allowed, as long as you do the same to both sides. So I'm repeating the step there on the left-hand side. Now, by the law of logs, if you have two things multiplied together within a log, you can separate them out by adding. So I can separate this out like so. Remember, x is my variable. And then by my next law of logs, I can take the n here and bring it to the back, to the front. That gives me then the natural log of a plus n ln x. And this is all equal to the natural log of y, like so. Now you're probably wondering, what use does this really have in showing what's going on? Well, if I rub this out now, just take what we have on the left-hand side just here, you'll notice it's written in a very particular way. Remember, the natural log of a is just a constant, and n is just a constant. That's what we are told in the question. I don't want to do that. I want to go back here. There we are. So what we can do is we can rewrite this as the natural log of y, so we keep the left-hand side the same. Because n is a constant, we can use any letter for it. So I'm going to use the letter m, ln x. And instead of having the natural log of a, I can just use any letter to represent that because it's a constant. So I could put c. And notice we can rewrite this in the form of y equals mx plus c. The only difference is instead of having y, we have the natural log of y. And instead of having x, we have the natural log of x. And what this statement shows is if I take my data for x and y and find a natural logarithm of it, then we will actually form a straight line. So this explains the part down below, that if we plot the natural log of all the y values, and we plot all the x values, but naturally logged, we'll find it gives you a linear relationship, that there's a straight line that connects the natural log of x with the natural log of y. Okay, now that's the theory behind it. In the second video, where we look at exponential and logarithmic models, you'll notice that the relationship is between y and ln x, or the relationships between x and ln y. But in this video, we're going to focus just on power models, where if we take the natural log of all the y values, natural log of all the x values, and then plot them on a graph, we'll find that they form a linear pattern, they form a line, or very close to a line. And that's why we can use then the power model. That's the theory. Let's do some examples. So with this one, we've already given that it's linear between ln f and ln t, and we need to work backwards to work out what the actual power model could be: t squared, t cubed, t to the power of 4, t to the power of 0.5 is. So this comes from the textbook. I'll go through this example nice and carefully. Now, we want to approach this in the same way that we do a straight line. So remember, for a straight line, we have the equation y equals mx plus c, where m represents the gradient, the steepness of the line, and c represents the y-intercept. Now, we know the y-intercept already, so we have that as 0.6, and we can actually work out the gradient by using the gradient formula in the formula sheet, which is y2 minus y1 over x2 minus x1. This is in your formula sheet. And the two coordinates we're going to take are this one for our x2 and y2. And this coordinate, well, this is actually a coordinate, remember, because the y-intercept has x as 0 and y as 0.6. So we're going to use the gradient formula on these two coordinates. Now, if we work through the arithmetic, we have 6.6 minus 0.6 all over 3 minus 0. And if we work this out on the calculator or in your mind, we'll get 2. So what we're saying for this specific line, ignore the ln for the moment, the equation of the line, if I was to take it as a normal y equals mx plus c question, would be y equals 2x plus 0.6. So far that looks like kind of normal. However, we do not have x and y on our axes. What we have here are ln f and ln t. So where we see a y, we need to replace it with ln f, natural log of f. And where we see an x, we need to replace it with the natural log of t. Okay, so we can work backwards to find what the power model is. So I'm going to write this in magenta, in cyan, very bright, apologies. So I've replaced the y with ln f, and I'm going to replace the x with ln t, like so. And everything else I'm going to keep the same. So the 2 stays the same, the 0.6 stays the same. And now what we're going to do is get f on its own by using natural log laws and log laws in general in reverse. So pay attention carefully to this part. ln f is going to stay the same. We're going to use the idea that we can take the 2 in a log and bring it to the back. So we can rewrite this as ln t squared. And the probably strangest step of the whole operation here is that 0.6 can be rewritten as ln e to the 0.6. Now you're probably thinking, why is that the case? Well, remember, ln is the same as log to the base e. Remember, ln is exactly the same as this. And if I write this as e to the 0.6, these all cancel, and I get the answer as 0.6. So what I'm doing here is I'm unsimplifying 0.6 to give myself ln e to the power of 0.6. The reason I do this is I can now combine the two logs together. So again, working in reverse to what we saw in the first slide. So natural log of f is equal to natural log, and now I can just times these two things together. So e to the 0.6. This takes familiarity with using log laws. And now because I have natural log something equals natural log something, only at this point can I then cancel the ln's. That's okay. What we're doing is raising both sides to the power of e, but essentially it has the effect of cancelling. And then we get f equals e to the 0.6 t squared. And this is where our calculator comes in. We can work out e to the power of 0.6. So if I go to my calculator, yes, I have it very conveniently here. I can just go normal scratch pad and E is down here. This is a convenient button, and we just type it in and we generate 1.82. So we can pop in 1.82 with this value, and we'll notice that our actual model here is a quadratic in this case, so 1.82 t squared. So these particular values on this particular linearized graph represents a quadratic. Now what's trickier, and we'll look at this in our second example, is when you have a set of data and you need to work kind of forwards. So you need to linearize it to prove or to show that a power model is applicable, and then we work out the particular power model that is applicable to that data. Okay, you will have a chance to practice a few questions in a moment. So let's go through our perhaps slightly trickier question. There's the answers. If you'd like to pause the video at that point and then just have a look. We're going to do this one together, which is much trickier. Now, the first part of the question wants you to draw a scatter diagram for S against N and ln S against ln N. Now, I'm not going to waste your time by drawing a scatter diagram for these values. If you do this, you will get this graph here. So you'll see there is a slight curved element to it. Okay. What we're going to concentrate on is working out these values here to show that if we find the natural log of S and natural log of N, that it forms a linear graph. So keep these values in mind. So we're going to use those values and we're going to use our GDC to work this out. So I'm going to keep that there. I'm going to generate on my GDC. I use a TI Inspire here. And we're going to create lists and spreadsheets. And I'm going to label this N. That's going to be my first row, and this S will be my second row. And what I'm going to do here is I'm going to find the natural log of all of these numbers. So this is going to give me the ln, natural log of all the N values, and then natural log of all the S values. The way I do this is the same way you do it in an Excel spreadsheet. So you type in equals ln, open brackets 4, enter, and then you'll get the natural log of 4. And what we're going to do is we're going to do exactly the same thing to all these values. So I'll do this as quick as possible, but you can match your values to mine to make sure you're getting the same thing. ln 14, ln 18. And the high-level applications course is a lot of GDC work. You need to be very happy working these things out. So what we're testing is your understanding of what's going on, not that you can calculate very long, arduous things. So 12.6, good, and equals ln 14.2, and then we've got equals ln 15.9. Okay, so then we've generated all our values, like so. What we do at this point is, on my TI Inspire, the way I do this is press the on button. I click on this button here, which is going to bring me to a scatter graph. But notice the points are not in the right place at the moment. So we need to say what variable on the bottom, which is going to be N, and what variable on normally the y-axis, we're going to put S. And you'll notice that you actually get this straight line appearing, which is what should happen. And this corresponds to this line here. Okay, so you could just plot this or take a screenshot and pop it in. So this is the graph of ln N and ln S, these values plotted on a graph. Now, the tricky part is, why do we actually need to have this? Now, the explanation of why S and N are related by a power model, so let me just go into this quickly. So the explanation here is that the graph of ln N and ln S is linear. And if ln S and ln N are linear, therefore it's a power model. And we'll look in the second video on when, say, S and ln N or N and ln S are linear, then it gives you a different kind of model. And this is what we're building up towards. Right, part C is working backwards and now working out the actual model, the equation connecting N and S, which is going to be a power model. So let's come out of this quickly. The way we do this is we're going to generate a regression line. So the way we do this is go to Menu, Analyze, Regression, and we just want a normal show linear regression line, and then you'll generate the final things here. So we get y equals, I'm writing this down here, 0.3958. I'm going to take 4 decimal places, x plus 1.6181. So I'm going to write this down on the PowerPoint, and then we're going to put in the natural logs like we did in the previous question. So we get y equals 0.3958x plus 0.6181. And I'm going to say this is by GDC. And now we need to realize, well, this is not y and x like we know it, but it's the natural log of s and the natural log of n. So where we had a y, we're going to put the natural log of s. That's our y values. And then where we put an x, we're going to put the natural log of n. This is where we put in the natural logs. And we do this in exactly the same way, working backwards to work out the power model. So these steps will be near enough identical to what we just did in the previous example. So our first step is to bring the 0.3958 to the back. So we get natural log of n to the 0.3958. We're going to transform 1.6181 to ln e to the 1.6181 using the same trick that we looked at before, because these two things cancel. The reason we do that is that we can now combine the logs together. Hopefully everything's going to fit in. I'm confident it will. So we get e to the power of 1.6181 n to the 0.3958. Now we can essentially cancel the logs, because you've got log this equals log this. And I'm going to work out now this number here, so e to the power of 1.6181. So I've got a Casio as well, often very useful for doing these kind of small operations. And you can look at the board as well. Of course, we get 5.04. And let's put another decimal place in there, 5.043. And this is the model that connects the two things together. 3958. Okay, and we're done. This is question C. So we've now connected up the variables of n and s. And what they like to do, applications, is get you to use what you've just worked out in a context question. So typical substitution question. Predict the maximum speed of the canoe if there are 8 rowers. So we're going to put in n is equal to 8. So we just insert that into our equation. So s is equal to 5.043 to the power, 8 to the power of 0.39. Okay, and if we pop that in, so let me just come out of here. I think I worked this out before. Yeah, 11.5. So you can type that into your calculator, say calculation. You get 11.5. I'm always rounding to 3SF at the end. Kilometers per hour. And that's the 3SF. And if we look at the data, that kind of makes sense. H should be somewhere in between here. It's not linear, so it's not going to be halfway between, but it's only going to be in between 10.3 and 12.6. And because we're interpolating, so what that means is this value n equals 8 lies within the data set, then it's quite a reliable prediction. If it lied outside, so say we looked for this for 20 rowers, for example, then it wouldn't be such a reliable value from our model. Okay, so by all means, take some time to go through this. This is not the easiest topic in the world. This is high level only, non-linear modeling. So once you think you've got the idea, if not, go back, listen to me again. I'll keep going through it. It's a great thing about YouTube. You can keep pressing that play button until you get it. So the answers are here, so you can check your answers. This here, if you don't have TI Inspire, this is the instructions for a CG50, the Casio, if you want to use that as well. So I'll leave that on the board for 5 seconds and take a slurp of tea. Okay, and have a go at these questions. So question 1 is very similar to the very first example that we did. Question 2 is similar to the one that we just did just now. So I'll pause the video if you want to go through these questions. Okay, and if you want another question along the same lines of what we looked at in the last example, so it talks about the reliability in the last part, which I mentioned, even though it wasn't in the question, in the example as well. So you want a little bit of a challenge, have a go at question 3. Okay, and the answers for questions 1, 2, and 3a are on the board. Strictly speaking, if it asks you to obviously draw the scatter diagram, by all means please do, for the variables p and a. But it wants you to look at this linearized model. As you can see, LNP and LNA appears to be linear, but notice in this case that our linear model is actually a negative. So when we actually form our model, notice we form our model here, that your index will actually be a to the power of -1, to keep that in mind. And because we're interpolating, because we're looking for value inside our data set, the estimate is reliable. Okay, hopefully that video has answered a few questions you had about high-level nonlinear modeling. In my next video, we'll look at exponential and logarithmic graphs. They work in a very similar way. This is why I'm going to put the 2 topics together. Before then, we decide, okay, how do we decide which model that we use? All right, I enjoyed putting this video together. Please like, please subscribe, and I will see you next time. All right, bye-bye for now.